This is a follow-up video of the video Can we take a picture of the deep earth? Here, I'm going to address two questions. How to define fishes for image logs from carbonate reservoirs. How to make a deep neural net do image log classification for us. Now, let's look at the first question. We defined 5 mutually exclusive species for carbonate reservoirs based on two criteria. They are the geometric attributes of laminations, namely the degree of parallelism and continuity, and the occurrence of shrubs. As shown here, species 0 is parallel thin laminations with branching shrubs. Species 1 is parallel continuous or discontinuous laminations across the borehole without shrubs. Species 2 is faint incomplete laminations or transparent beds. Their characteristics are clear in the stick figures. On the whole, species 0 to 2 contain weak artifacts and noise. From species 0 to 2, the degree of parallelism and the continuity of the laminations decreases, while the matte content increases. Thereby, the gamma ray value increases. Species 3 is chaotic species without clear laminations. Stromatolites are classified as species 3. Species 4 is strong artifacts that conceal all underlying structures. Species 5 to 7 are less certain species 0 to 2 due to the disturbance of artifacts. During training, a weight below 1 is assigned to them to represent their lower certainty in manual labeling. The last class contains all uncertain sections with entangled features and artifacts. They are not labeled, excluded from training, and used for blind tests after training. It's time to answer the question how to make a deep neural net do image log classification for us. The first step is to prepare training data. The first set of training data is manually labeled field data of 8 whales from the Brazilian pre-salt region. It took me 1 month to label the 8 whales because I had to go over them many times to ensure the consistency of my labels. Despite that, the resolution of the manual labels is much lower than the pixel level resolution required in depth-wise classification, and the manual labels are not perfectly consistent and accurate. To improve the quality of the training data, we augment them with synthetic data, which are noise-free and well understood by us. This equation describes the process to synthesize image logs. Basically, image logs are the superposition of the convolution between various 2D features and their feature maps. The 2D feature entries to compose the image logs are summarized in this table. Here are examples of synthetic species 0, species 1, species 2, and species 4. The structure of our deep neural net is shown here. It is modified from the well-known UNet for image segmentation. The input data have 3 channels, corresponding to the static image, the dynamic image, and gamma ray logs. The output are depth-wise classification of the input images. Moreover, the network is trained with a mixture of field data and synthetic data. After training, the DNN provides 99%, 87%, and 70% classification accuracy for the training, validation, and test sets respectively. Here is the test section from whale 0. From left to right are the static image, dynamic image, raw DNN prediction, label, DNN probability, and final prediction. Specifically, the final prediction is obtained by removing the thin and less probable sections from the raw prediction, such as this thin section in the middle. Overall, the DNN prediction agrees well with the label. Moreover, the DNN correctly identifies some fine-scale species ignored by the human interpreters, such as the top thin species 2 that is mostly transparent, and the lower thin species 1 with faint sinusoid. This is an uncertain section from whale 4. Its interpretation is impeded by the strong vertical artifacts. First, the DNN correctly identifies the borer breakout in the red brain. Second, the DNN prediction is very reasonable in that the smooth and transparent sections are identified as facies 2 and the rough and fuzzy sections are classified as facies 0. To summarize, in this study, we propose to train a deep neural net with manual labels to provide instant depth-wise facies classification for image logs. The trained DNN generalizes well to the test set and the uncertain sections. It outperforms manual classification with better consistency, higher resolution, and much higher efficiency. The DNN predictions for the uncertain sections serve as a good reference for human interpreters to better identify the facies. It is the end of this video. Thank you for your time.